For those of you here right now, I want to quickly just talk about something about Wolfram alpha that we discussed from the first lecture. If you, on your keyboard, if you want to type in an exponent, you use this symbol. This is not a good and if you, multiplication is, as you probably know, is an asterisk. If you're confused about how to enter stuff into Wolfram alpha, you can basically, the way you'd write it out on paper, it's the same except for multiplication you use an asterisk. So in case you need to, other than that, Wolfram alpha is also, as I mentioned, sort of like Google. It'll correct you if you make a mistake, or it'll try to figure out what you mean. But if you have trouble with Wolfram alpha, you can come to us. So I'm assuming everyone's here. Today we're going to talk about electricity and magnetism. So I'm going to start out with asking you a question, which is, so we've learned about, on sort of the surface level, we've learned about gravity. So I want to ask you, from what you know about the forces of electricity and magnetism, what do you think is the difference between those and gravity? Do you have any ideas? Okay, so you can talk with your partner for a couple seconds, and then I guess say differences that come to your mind. Whatever you get there.
Can you repeat the question?
So from what you know about gravity, from what we've covered so far, what do you think is the difference between the forces of gravity and the forces of electricity and magnetism? You've probably played around with magnets before. You felt how magnetic forces work, and then of course you live on Earth, so you probably know about gravity. So based on your knowledge of that, how are they different and how are they the same?
That's true.
Remember the difference? Magnetism isn't dependent on the size, the mass. So that's the difference.
Does anyone have any ideas yet? Yeah.
Gravity is only attractive, not repellent, but electromagnetic forces can be repellent.
Okay. Yeah, that's the most significant one. Gravity is you only feel gravity attracting objects together because gravity doesn't have a repulsive equivalent. And the biggest difference between electricity and magnetism and gravity is probably that electricity and magnetism, you can have magnets repel each other. That repulsive force does not exist in gravity. Any other ideas? Yeah, that's probably the most significant one, so if you got that. So I'm going to give you some examples of electricity that you've seen, on the So you've seen like the cloud and then lightning. That's an example of electricity. Like probably seen like static electricity. If you rub your a balloon on your hair or something, your hair will stand up on end. That's an example of static electricity. And then this you might not have encountered in your everyday life, but galvanism. Galvanism is related to the flow of electricity. So people in the 1800s basically observed that if you had two wires and you passed electricity through them, you passed electricity. I'm going to draw an arrow to show which way you're passing electricity through them. They observed that these wires would attract towards each other. So those wires would actually move closer together. And as soon as you stopped the current, those wires would come apart again. So this begs the question why, right? And then, so galvanism is commonly used in things like your cell phone, like various different kinds of electronics. And then of course we have magnetism. You've all probably felt bar magnets. You've seen how magnets, like if you put a north pole on a north pole, you get repulsion. If you put a north pole on a south pole, you get attraction. So likes repel and opposites attract. So why exactly do these forces come about? And how like you probably noticed that there are some similarities between electricity and magnetism, but how exactly are they related to each other? In the title we've said electromagnetism, so they're clearly related in something. We're going to start with charge and how exactly charges relate to electricity. So when we're talking about electricity, we're saying that there's this stuff, this mysterious stuff basically, which interact with the electric and magnetic forces. Especially, and electricity is basically a movement of charge. So charges can be both positive and negative, just like sort of analogous to like magnets. You can have positive charges, and positive charges will attract negative charges. So these will attract. And like charges will repel each other. And so same with like negative charges. So this isn't a particularly good description of what charges are, but we'll sort of describe it better as we go along. But the way that these charges attract and repel is through the electric force. And this is important because this describes how the electricity part of electromagnetism works. So, and then we have the magnetic force. So this is electricity. And then we have magnetism. And so magnetic fields or the magnetic force works slightly differently. With bar magnets, the south and the north pole next to each other will attract. And like poles will repel. And so you get the picture. But the important other thing is if I throw a charge, one of these charges, near a magnet, and I shoot a charge near a magnet, people also observe that the charge will move through the magnet. It'll actually deflect. And so, importantly, the magnetic force also acts on moving charges. And this sort of suggests that there's a link between the electric and magnetic fields, aside from just like the fact that they sort of look separate. So I'm going to now describe a couple concepts that are useful in order to visualize how magnetic forces and electric forces work. And one of the important visualization tools that we use is called a field. So you can think of a field as, it's imaginary, but it's a useful way to visualize how these things work. A field has a magnitude and a direction in everywhere in space. So if you have like a magnet, and a field, for example, can describe how you feel a push and a pull from that magnet. And so if you're really close to that magnet, you would feel a push away from the magnet, assuming you're a like magnet, right? You would feel a push away from the magnet, directly away from the magnet, and you'd feel a really strong push because you're very close to the magnet. The farther away you get from the magnet, the less strong that push becomes, and the direction will also change. And the same applies to like an electric field. So if you have for the case of electricity, let's say this is a positive charge. An electric field might look something like this. So everywhere around, close to the electric field, you feel a strong push. As you get farther and farther away, you'll feel a weaker and weaker push, so the arrows will get smaller and smaller. You can basically think of that as saying, as you get farther away from this electric charge, the amount of force that you feel will get less and less. And if you come to the discussion section, you'll see, we'll give you a picture of how fields are on magnets. Everywhere in space, you have direction and you have an amount. So you have like a magnitude. And the amount relates to how strongly you feel a push and pull, and the direction relates to what direction you feel a push and pull. So now I'm going to describe the second important concept that we've already gone over. We've gone over in last lecture, but I'm going to show you how it's also applicable to this, and that is the concept of a potential. So you have hills, and we can sort of visualize the same concepts with either fields or potentials, whichever is more useful for this specific problem. So in order to show you how this works, I'm going to first draw a bunch of extremely messy math. So in the 1800s, people were experimenting a lot with electricity and magnetism. As soon as they figured out how batteries work, you can basically generate electricity through batteries. People started shooting electricity through everything they could. They started experimenting with magnets. They saw the link between electricity and magnetism, but the link was sort of vague at best. And so there was no way to codify how exactly electricity and magnetism were related until James Clerk Maxwell came along. And he basically looked at exactly how these experiments were working, and he wrote out a mathematical formalism to predict and describe exactly what happens with electricity and magnetism. So I'm going to draw it out in all the detail, and I'm going to caveat this with, I don't expect anyone to have seen or understand the math, exactly how the math works. And so I'm going to give you a legend, and I'm going to write it out in English, basically, so that you can understand how what all of these laws is talking about. But for now, this is going to look very complicated.
Can you write it bigger?
Oh yeah, okay, sure. Oh, by the way, another thing I should say is, I highly encourage you guys to think about questions, because I learn best by questioning. So if you guys have any questions, you should feel free to ask. Is this big enough? Is that big enough? Okay. Okay, so for those of you who are new to the class, by the way, like we're going to be talking about, we don't expect you to understand everything that goes on. We're sort of covering interesting and like important stuff in physics, but we're also not necessarily covering it at like, we're not covering all of the simplest stuff because the simple stuff is often also the boring stuff. So in order to like talk about more interesting stuff, we'll also have to get complicated, and that sometimes means stuff that you might not understand, but that's okay. We don't expect you to understand everything. But I'm going to go into, so whenever you see like an upside down triangle and a dot, I want you to read this as this is called an operation. All like this, the upside down triangle and the dot, the upside down triangle and the cross, and this weird like backwards or like mirror reflected 6. These are you can sort of think about them as operations that you apply to something. So you would apply this to something, right? And this could be read as where springs out. And then for del cross, this can be read as where curls down or twists around, whatever you like. And then this or okay, so these are the most important ones. So let's start with this. I'm also gonna. There are a lot of other symbols here. These are Greek symbols, but they all denote something important. So we'll go over. I'll also write down what they mean on this side. So this is charge. Like a lot of you might have encountered pi. Pi is a constant, right? And you can sort of put it into equations to like show how amounts relate to each other. There are a lot of other constants in physics, and so we don't need to worry about those constants too much, but I'll write them down. So this is another constant, and we won't worry about what that constant is. And then, oh yeah, sorry, this is another constant. So that's just, it sort of relates how a certain quantity will like how much of a certain quantity equals a value of another quantity. So this can be read as where the electric field springs out. So remember earlier I drew a charge, and I drew arrows pointing all like out of the charge, right? So this equation is saying where the electric field springs out of some point, there's a charge at that point. That's what the first Maxwell's equation says. And so, for example, in this example, you can see the electric field is springing out of an area, and that area is where your charge is. So that sort of you can. The other thing is the magnetic field. B refers to the magnetic field. Where the magnetic field springs out is 0. So basically the magnetic field never springs out of somewhere. You're never going to see a magnetic field that looks like this. That's the important second point. The third equation says where the electric field curls around, or where the electric field twists, is where you're going to see a change in the magnetic field over time. So where the electric field twists around, you're going to see a change in the magnetic field over time. And the last one is where the magnetic field twists around is, this is like a more complicated case, but essentially this means where the magnetic field twists around, you're going to have a changing, you're going to have charges flowing, plus another factor, which we won't go into for now, but I'll get back to it in a bit. I want to talk about how this relates to potentials now. Or actually, I think I'll hold off on the potentials for now. I'll get back to that in a second. But does anyone have questions? Yeah, sorry.
Can you please translate one more time number 3 and 4?
Okay, sure. So number 3 says.
Actually, could we, for number 3, what does the symbol on the left stand for? Like the upside down triangle cross?
Okay, yeah. Yeah, based on the key, can you try like figuring out what it means? Where E is, where E.
What was E?
Is the electric field.
Electric field.
Yeah, I'm going to write that down as well, sorry.
So where the electric field curls around.
Okay. Yeah, I realize this is a lot, but remembering the details in the long term isn't that important. What I want you to do for now is, I think it's a useful exercise to go through this like very complicated looking math and understand at a qualitative level what exactly each of these equations means. Even if you don't retain the information, it's useful to at least like understand it on a surface level for now. So can you go through equation 3 based on the key and like put it together for me real quick?
Where the electric field curls around, there is a change in the magnetic field over time.
Yeah, exactly. So if you ever see an electric field, like this is an example of electric field, but if you ever see an electric field that looks something like this, or that looks like, that twists around somehow, then you can sort of say, at this point, there's a magnetic field that's changing. And we'll get into where exactly we use that. But for now, like that's going to be how we explain the third Maxwell's equation. Oh, and this is sort of so I went in at the beginning. I said how flowing electrons or moving electrons are an example of current, right? Of electricity flowing. And so J will represent a current. Or moving charges. So in this last equation, you asked me to go over the last equation. If you see a magnetic field curling, that's usually it's a current. Ignore the constant for now. It's a current plus some constants and a changing electric field over time. So again, if you see a magnetic field curling, it's a current plus a changing electric field over time. That's what the last equation represents. Any questions any more questions on Maxwell's equations? So right now this sort of seems very useless, unmotivated, but by the end we'll get back to why Maxwell's equations were so important. And yeah, in the next lecture you'll also see the big problem that this set up. But I can set up the problem in this lecture. So I'm gonna like jump around to a slightly different concept for now. And that's the concept of insulators and conductors. Actually, yeah, actually, I'm going to talk about. So, we talked about lightning in the first part of the lecture, and so in lightning you have a cloud. I'm going to drop that a cloud. And when clouds rub against each other, charges come off of one cloud and deposit onto other clouds. Basically, there's when clouds move past each other, you can end up with clouds that have an overabundance of positive charges, so they start looking like this. And when you have a cloud that looks like that, at some point you end up with lightning. And the question is, why exactly does that lightning happen? And so in order to show how this is, I'm going to talk about electric fields in terms of the potentials we discussed from the last lecture. And so if you guys remember, we for gravity we told you about like hills, and we talked about balls rolling down. Yeah, sorry.
Just going back to the cloud, what happens to the clouds that have an overabundance of negative charges?
Same thing. Same thing. Yeah. And yeah, they're also when one charge gets an overabundance of positive charges, another cloud will end up with an overabundance of negative charges. Yeah.
Well, how do you explain thunder? Because in thunder, there's not necessarily lightning. Or is there?
Yeah, there is. I think thunder is. If you see thunder and not lightning, chances are it's lightning happening somewhere from a cloud to another cloud, or like you can't necessarily see the lightning, but lightning will exist. Thunder is like on a qualitative level, lightning is the flow of those charges from the cloud to the ground. And thunder occurs because that flow of charges is so violent that it actually it ionizes the air. It takes the electrons, or it takes the atoms. It forces the electrons out of the atoms, and in that process, it superheats the air to an extremely high temperature and sort of pushes a sound wave around, or like it pushes a sound wave from the lightning, and that creates the thunder. So we're going to go into how exactly the charges get to, why the charges actually need to move from the cloud down. Yeah?
Yeah, I'm curious how the charges are being localized in one area when they should be repelling each other. Right?
Yeah. So this is a concept called triboelectricity. So if you ever rubbed a balloon against your head, you sort of felt it. But it turns out that when you rub objects together, you're basically taking atoms and rubbing them against other atoms. And it turns out when you do this, so atoms have your proton, and then you have your electron, somewhere around your proton, right? And when you rub two atoms together, you're basically taking the electrons and you're forcing them against each other, right? And you're moving them past each other. And when you do this, certain materials can tend to lose their electrons more easily. Certain electrons tend to gain electrons more easily. And so when you rub two different materials against each other, sometimes the electron will lift up off of one material and deposit onto the other material. So if you rub a balloon against your hair,
I might add, for reasons that are not very well understood.
Yeah.
An active field of research.
Yeah, this is true. But the electrons will sort of lift off of your hair and deposit onto the balloon. And the same happens in clouds. If you have ice in one cloud and you have water in another cloud, and the clouds rub against each other, except this is happening on much more massive scales. And so electrons will lift off of one material and deposit them on the other cloud. And so I'm gonna quickly talk about potentials. When you have something that's charged, we act as if that's the top or bottom of a hill. The difference between gravity and the potentials that we're going to use for electricity and magnetism is, as we mentioned in the beginning, gravity only attracts, whereas electricity can both repel and attract. So how do you show that? Basically, a negative charge will roll up a hill and will try to get to the top of the hill, whereas a positive charge will roll downhill. As like your intuition is. And the tops of hills represent the charges that you have. So this is another way, like fields, this is another way, it's sort of an equivalent way of visualizing what happens around charges, what happens around, and around magnetic fields as well. So if you have like a positive charge, another positive charge will tend to roll down the hill, so it'll tend to roll away from the positive charge. A negative charge will roll up the hill, so it'll roll towards this positive charge. And then valleys represent negative charges. So if you have a positive charge, they'll tend to roll down the hill, and negative charges roll up hills, right? So negative charges will try to roll away from the valley. So the concept of potential becomes useful if we're trying to figure out why situations like this arise. And so we can draw this as like a big hill. And you have a ton of positive charges here. And all of those positive charges are like, they're trying to get away from each other. And so they all roll down towards the ground. And this is one way of visualizing how lightning works. And so another way you can see this is if you have power lines. So if I were to have these power lines, so if I were to just like sit on top of say both of these power lines were carrying a ton of positive charges. And I were to somehow like climb up and just like sit on the power lines, what would happen to me? I'm not touching anything else other than the power lines. Or let's say I were a bird, right? You've seen birds sitting on power lines. What do you think happens to them?
They're usually fine.
Yeah, why are they fine? If we were to look at it in terms of like the hill diagram, it starts to make sense. This is okay because you're basically like, it's like sitting on the edge of a cliff. Like I'm on the edge of a cliff. I'm not in trouble unless I get pushed off the cliff, right? So so this is me, right? And then this is the ground. And this is the cliff. But if I'm not in contact with the ground, if I'm nowhere near the ground, I'm perfectly okay. The issue is when I try to get down, if I touch the ground and the power line at the same time, now I roll down like the cliff and I hit the ground, and that's when I don't recommend you try this at home. Yes?
So if you're holding onto the power line and you're touching the ground, he's touching, or this person's touching the ground.
Yeah.
Will other negatively charged particles come to you?
Yes. I mean, negative charge or the positive charge particles from this will flow towards the ground. In this case, negative. Yeah. You can also think about it as like negative charge particles will come up, and that's actually what does happen. Negative charge particles will come up from the ground and neutralize the positive charges up here. Right?
Is that what causes like the shock?
Yes, that is literally what causes the shock, because you have a current And what is current? Current is the flow of charges, right? So you have like negative charges, and they flow up and meet the positive charges. But the important thing about this, remember when we talked about potential from last lecture, we were talking about the movement of energy, right? We were talking about release of energy. When something flows down, rolls down a hill, it's gaining kinetic energy, right? And it's losing its potential energy. And importantly, when the ball rolls down the hill here, there's a release of energy. The energy is what will do you in if you try this. It's what will kill you, right? There's going to be a very, very large energy release when you touch the ground, and it'll fry you. But another important thing about this is when we're looking at potentials, let's say you have a potential that looks like this, right? And you have your ball up here, right? Let's take another situation where we just move everything up. We shift everything up, and I'm going to draw this slightly farther down. And another situation where everything is up higher. So which of these, is there a difference between these two functionally? So raise your hand if you think there is a difference.
Could you pull the board up?
Sorry, yeah.
Maybe like a podium.
Is that good?
Yeah. Or no button.
Okay, so the only difference between these two, I'm going to erase this stuff so it's not as confusing. Is there a difference between these two? Okay, so raise your hands if you think that there is no difference between these two. Okay, raise your hands if you think there is a difference between these two. Okay, so I'm going to have someone, if someone wants to volunteer to motivate why they think there is a difference. Anyone? Any volunteers? Why do you think there's a difference between these two situations? Okay, so I should make the problem statement is that we move everything up by a certain amount. Yeah?
Okay, this is your zero mark, I guess. If you want to plot that at the end of the bottom.
Yeah, yeah.
You guys refer to that as zero.
Yeah, yeah.
You're just moving that zero up. If you're the same distance from your zero or your from the bottom.
Yeah. So that's actually that's a very good description. If you move your zero up and you move everything else up as well, you end up having the same situation basically, and the ball is going to roll down the exact same way. So yeah.
Is this the same concept as translational symmetry?
Yeah, it's a good connection. This is another example basically of a continuous symmetry, right? And we learned from the last class that continuous symmetries lead to conserved quantities, right? Through Noether's theorem. Can anyone take a guess at what symmetry? So the symmetry here is that no matter how much you move these potentials up and down, it's going to look the same basically. Your situation is going to be the same. So can anyone take a guess, a random guess as to what quantity this leads to a conservation principle? So so far we've done conservation of energy, we've done conservation of momentum and conservation of angular momentum. What do you think that this leads to a and for you too, I know you haven't gone over this yet, but don't worry. Yeah. Yeah, you're right. So this is called a gauge transformation, and it leads to and the fact that that there's a symmetry is called Oh, sorry, one is positive. They're both positive. They're both identical situations. The only difference is we shifted one up vertically. So I could redraw this to make it slightly clearer. Yeah.
So I get that like in like the picture you can show it moving up, but what does that mean? Like what does it actually mean to move the?
To like move the potential up, it just means like, for example, this is like, let's say this is like, I guess you could think about it as like, we'll actually demonstrate this slightly better tomorrow in class, or sorry, in discussion on Wednesday, but that's a good question. It effectively means you are changing, you're moving everything up. So let's say I was at like, there was a wire at like 5,000 volts, right? If 5,000 volts were flowing through my body as well, I could touch the wire and nothing would happen to me. The problem would arise when something that's not 5,000 volts comes into contact with that 5,000 volt wire. Then you get fried. So, so by pushing everything up, we can think about that as like if you have a wire that's 5,000 volts and I was 0 volts and I touch it, I get shocked. Let's add 5,000 to everything. Now let's say I'm 5,000 volts and that wire is now 10,000 volts. And I get shocked by the same amount because I just moved everything up. So yeah, but we'll explain that slightly better in discussion. We'll actually demo in discussion. Yeah, remind me to explain that question in detail if I forget about it on Wednesday. So actual gauge symmetry, this is like an oversimplification. Actual gauge symmetry is slightly more complicated, but this is like the basic idea behind it. And this is importantly why in our universe the amount of charge is conserved. And there's a reason why this is important. Electromagnetism couldn't exist without charge, right? And this basically means you can frame a lot of problems by thinking about how charges, thinking about things from the perspective that charges could not have been created or destroyed. Charges can never be created or destroyed. So here's a question: if there are no charges, I want you to look at Maxwell's equations. Look at that. Oh yeah. I want you to look at Maxwell's equations for this with a careful eye, and tell me if there are no charges, can E and M? Is there anything interesting that comes out of E and M, or are all of the equations just zero? So it might be helpful to discuss with the person next to you, and then I'll give you a couple minutes to think about that question. Is there anything that's interesting that happens in Maxwell's equations, even if your charges are zero?
Put another way, if the charge and current is zero everywhere, does that mean the electric and magnetic fields are boring?
Yep.
Right. So for example, like the electric field could be constant everywhere, and actually the equation would still be true. So that's kind of boring. Is there like a not boring answer?
So it's probably, it might be a bit difficult to interpret these, but try the best you can. Well, one thing I would suggest you do is write down so if charges don't exist, if we don't have any charges in our universe, which of these things over here are zero? So we have.
Sorry? That's literally this room. If you want to think about it, like there are no charges in this room. It's an empty room. But do Maxwell's equations still apply to this room? And if so, how?
Like is there anything interesting that Maxwell's equations say happen in this room even though it's empty? Or it doesn't have charges in it, right?
Just talk among yourself.
Yeah, yeah. And then if there's no charge, then that means there's an electric field. That'll persist. 4 0 1.
So the question is and current
If charges don't exist in our universe, yeah, basically. And so like it might be helpful to write down like out of I'll give you the options. There's this. Right, there's this. They're all of the quantities in the equations above. Which of those quantities do you think is 0? If charges don't exist, which of those quantities do you think is 0? And it would be helpful to write them down so that you can reference them and figure out how the equations work.
So if there's no charges, then maybe there's no electric field. Because the electric field depends on charged particles.
Does anyone have anything about the first equation? What do you think happens to the first equation if charges don't exist in our universe? So for this one, I would suggest you start on the right. So we know that that Greek letter that looks like a P, and that's a rho, by the way. That rho is equal to 0. So the right side of the equation becomes 0, right? So what happens to the left side of the equation when the right side is 0? Of course, the left side is 0. But what exactly does that mean? So start from there. When the right side is 0, that doesn't just mean the electric field is 0. It means something slightly different than that.
Neutral?
So the electric field spins out from.
Yeah.
Would it act in the same way as the magnetic field?
Would what act in the same way?
The electric field would act in the same way the magnetic field was since charge is 0?
Yeah, exactly. So the connection he's making right now is the second equation is upside down dot B is equal to 0. And if charges don't exist in our universe, then upside down dot E is equal to 0 as well. And so this is basically saying that the electric charge doesn't spring out from anywhere, and the magnetic field, the electric field doesn't spring out from anywhere, and the magnetic field doesn't spring out from anywhere else. But I want to particularly draw your attention to the last two, which are also the hardest ones to think about. What happens to the last two? Does anything change in the last two equations, number 3 and 4? Let's start with number 4. Can anyone think of anything that might change if charges don't exist? What happens to the left-hand side of equation 4? Yeah?
Well, J would have to be 0.
Yes.
There's no charge to move.
So if charges don't exist, J would have to. He's saying J would have to be 0 because J is a movement of charges, right? And if charges don't exist, they can't move, of course. So this term drops out. So you end up with this and this, but nothing there. Does 3 change? Raise your hand if you think equation number 3 is any different if charges don't exist. So raise your hand if you think it's different. Raise your hand if you think it's the same. Okay. Yeah, so you all are correct. It's basically equation number 3 is the same if charges don't exist in our universe. And equation number 4 is similar except without this part. So Maxwell's equations, not everything just becomes 0. So this means that if we have a universe in which there's no charge, we still expect something to exist. we still expect some interesting behavior. And it turns out this interesting behavior is something that we actually have in this room here right now. So you can sort of think about, we don't necessarily have any significant charges around in this room, but there's something related to electromagnetism that we have in this room that is pretty interesting. So I'm going to draw your attention to the third equation right now. So this is saying a curling electric field changes the magnetic field, or a curling electric field is a change in the magnetic field. And equation number 4, if we think the charges don't exist in the universe, right? So now a curling magnetic field is a change in the electric field. Can you guys see that? So let's say we introduce a small, we wiggle the electric field slightly. And we wiggle it in such a way that it curls the electric field, right? So this would, when we do that, that would result in a change in the magnetic field. Can we see how that works based on the third equation? So now the magnetic field is changing. And when the magnetic field is changing, I'm going to sort of hand-wavingly say that when the magnetic field creates a changing magnetic field that'll twist. So this will twist the magnetic field, right? And that twisting of the magnetic field then creates a change in the electric field. It starts changing the electric field. So as a summary, when we wiggle the electric field, that creates a changing magnetic field. And that wiggling of the magnetic field will in turn create a wiggling of the electric field. And so you end up with this chain reaction. Can anyone connect this to something that they've heard of before, that they think might be the same as this? Yeah?
Motors?
It's similar to the concept of motors, but not quite. The difference here is that, the thing you're on the right track about is, motors exhibit similar behavior, but we're talking about a phenomenon here. Yeah?
Is it electromagnet?
It's not an electromagnet. Again, I want to focus on the idea of a phenomenon here. So I'm going to give you the answer because this is really hard to get. Sorry, yeah. Not gravity. It's close, but not gravity. Yeah.
Wait. It's a bit probably bizarre, but is it light?
Yeah, you're correct. It is light. So we're in this room. There's no charges around in this room, but we do see light, right? So the universe isn't boring. And some of you might have heard before that light is an example of an electromagnetic wave. If you haven't heard it, you're hearing it now. But light is an example of an electromagnetic wave. It actually arises from Maxwell's equations. It's like Maxwell wrote down these equations and he noticed, there's a funny quirk about these equations. When I get rid of charge, suddenly I get this phenomenon where when I wiggle the electric field, when I oscillate the electric field, I end up with a changing magnetic field. The magnetic field then changes the electric field, which then changes the magnetic field, which then changes the electric field. And this idea is very similar to the idea of a wave. If you were to do the math completely out, you literally get the equation for a wave out of the solutions of this. And so he noticed that it behaves exactly like a wave. And so this is where the idea of light being an electromagnetic wave was born. And I want to draw your attention to one thing in particular, and that thing is these constants over here. So the asymmetry, if you were to think about it in that way. So this equation. So again, we're going in a universe where there's no such thing as charge. We're going to worry about charges. Okay, so the only differences between these equations are in the constants. So you can sort of think about this negative sign as being a -1 times this, right? And you can think about this as being these two random constants times this. And so this, when set out in English, this means that you have to change the electric field at a specific rate in order to get a changing magnetic field that then changes the electric field that then changes the magnetic field. So there's a really specific rate defined by these constants that if you change the if you wiggle the magnetic field, you end up with a changing electric field, which changes the magnetic field and creates this wave. And that rate is the speed of light. So I'm going to sort of, this is going to come back in the next lecture. But Maxwell's equations sort of imply that there's a fundamental speed of light. And it's the same everywhere in space. It doesn't matter where you are or what you're doing. The speed of light is always the same. And that speed of light is defined by these constants. It's defined by this constant in particular. And that's a very, very important concept that will come back next lecture. So make sure that's something that you write down. Yeah.
Is it fundamental because it doesn't depend on charges?
It is, yes, in a way that's the case. But I guess it's more fundamental because in the math over here, you have constants basically that never change, right? These constants aren't based on anything. They're like pi, right? So like, no matter where you are in the universe, the circumference of the circle relates to its diameter by pi, right? And so in the same way, like no matter where you are in the universe or what you're doing, these constants govern the relation between how you wiggle an electric field and how the magnetic field ends up wiggling in the same way. So in order to create light, in order to create the phenomenon of light, you basically need to wiggle things at the speed of light. And so the speed that the wave propagates is based on these constants. Yeah?
Does this only happen in the absence of charges, or does it apply to all scenarios, including with charges?
Well, that's a slightly complicated question, but I think the answer to that question is basically light is sort of, you don't need a charge in order to propagate light. Light can propagate in a complete vacuum in the absence of all charges, right? And the interaction between charges and light isn't something that we're going to really talk about, and it's not something that really matters. So for all intents and purposes, it means that even in situations where charges aren't involved, we can end up with light. In fact, that's where light is. That's where we see light, right? And so yeah, so in areas where there are no charges, where you don't have like an electron or something, you can still end up with light. Light can still travel. And so it turns out when you do the math, you end up with. So I showed you electric fields coming out of like an area like this, right? So electric fields can look like this, right? Now I'm going to show you how electric fields end up looking in a light wave. And this isn't a perfect drawing. These actually work in 3D, and things get slightly more complicated than this, but this is actually a decent way of looking at how the electric fields and magnetic fields look in light. Oops, sorry. I'll probably do that. Okay, so that's how the electric field looks, right? And I'm not going to draw as much of a magnetic field, but suffice it to say, it looks the same, except it waves in and out of the page. And obviously, I'm not an art major, so I'm going to have trouble drawing that, but I'm going to try my best. Okay. And so on. So these go in and out of the page. And so the electric fields, or the electric field and the magnetic field are like 90 degrees opposite to each other. If I were to look at this from this direction, that's an I. If I were to look at it from this direction, the electric field, sorry, so they would sort of look like this. And now I'm going to show you exactly what. I'm not going to do the math, of course, but the speed of light is given by c, a lowercase c. And I told you it's related to these constants. I'm going to say it's related to these constants in this way. You'll have to believe me for now, but we can explain this later. And this is approximately 3 times 10 to the 8 electric per second. This is an important number. Probably not going to have you memorize it, but it would be nice if you did. What?
So it doesn't come out exactly to the speed of light? Or does it?
It does come to exactly the speed of light.
Okay.
Yeah. Yeah. Is there something you know that I don't know?
I mean, you said approximately.
Oh, sorry. I meant that this is exactly this, but this is approximately. It's actually like 2.99 something. Yeah. The number is important. The important thing is that if you take these two constants, they will give you 1 over the square root of those two constants multiplied will give you exactly the speed of light. That's actually how the speed of light is defined. Or it's how these two constants are defined, however you'd like to look at it.
So is the speed of light defined for those, or those defined?
I guess either way.
Clarify, you can measure epsilon naught and mu naught.
Yes.
Mu naught. And then you can check that they're equal to the speed of light.
Yeah. So both are. The important thing to say is like both of these are measurable quantities.
Okay.
I can easily measure the speed of light by figuring out how far light traveled and like the math there. I can also measure these two quantities, and they're literally exactly the same. So it sort of proves it. So the takeaway message from this is that light is a consequence of electromagnetism, and like light is actually an example of electromagnetism in a way. And the last thing that I want to sort of go into is we have like light now. Can anyone think about properties of light that they might have like known about? Like if I there are various different properties of light, right? Yeah.
Just its luminosity.
Luminosity, yeah. So that's sort of it's related to the number of these or the amount of these waves. Like if you like think about them as C waves, like a more intense C wave is a wave with like a higher crest and like a lower trough, right? So you can think about that as relating to the intensity of light. Can anyone think of another property of light? Yeah. Color. Yeah. Color is an important other property of light. You can have red light. Some of you might have heard that white light is a combination of like all of the different colors of light, and this is true. So For, let's say, like, we're just talking about one specific color of light, like, let's say red light. That is actually related to something about the wave, a specific property of the wave. Your eyes will actually see this property of the wave, and that is the length between this over here, wavelength. So this is really important. This wavelength of light is the color of the light that you see. So you have red light. Red light has a longer wavelength. If you shorten the wavelength slightly, you end up with blue light. If you shorten the wavelength still further, some of you'll end up with violet light, right? Still further, if you shorten it, you'll end up with ultraviolet. If you continue shortening it further and further, you'll end up with X-rays and gamma rays, and like this. And if you lengthen it beyond what red is, you'll end up with infrared. You'll end up with microwave, and you'll end up with radio. So this is the basis of. So some of you might not have heard about this before, but radio waves, microwaves, X-rays, blue light, red light, they're all like the same thing. They're basically related to color. And so you can think about radio waves basically. Radio waves are literally just colors of light that you can't see that are well beyond red and blue. So I'm going to draw out the electromagnetic spectrum here. And it's useful to actually remember this, if you can remember it. Right, so I can't draw a rainbow, but if you were to visualize a rainbow here, this is visible light, right? I'm actually going to, I think vaguely between 300 and 700 nanometers, but I'll look it up real quick.
Yeah, red is 700.
What?
Red is like 720.
720, yeah. So 310 and 720, I think, is the common number. 380, okay. So at the farthest end of what you can see on this side, with your eyes, like the bluest blue light that you can still see, it would be around 380 nanometers. So this number is referring to the length of this wave. Is referring to the length of this wave, and this is 700 nanometers. So this is the length of the wave, right? On this side, these are still colors of light, but they're invisible to you. You have. I should write it up. You have infrared, and on blue you have what? On this side you have microwave. Okay, so this is called the electromagnetic spectrum. I'm going to write that in black. So whenever you like, and something that's interesting to do that if you want to like show to yourself that this is actually the case, if you take one of those TV remotes, so it turns out your cameras, your cell phone cameras sometimes are, they don't make them exactly like they make the human eye. So your eye pretty much stops being able to see, like if you go slightly beyond red, so you won't be able to see it anymore. But it turns out they can't make the cameras exactly like your eyes. So your cell phone cameras usually can actually see a little bit more into the infrared region. And it turns out that's exactly where TV remotes send signals to your TVs with, right in this region of infrared. So if you take a TV remote and you point your camera at like the front of the TV remote, usually you'll be able to see like light on your camera. Even though you can't see anything with your eyes, you'll be able to see light with your camera. And this is something you should go home and try. And it'll sort of prove to you that infrared is like right beyond red. And there's this whole spectrum all the way here. For radio waves, it's about, the wavelength is about meters. But let me look that up.
You guys know why? You guys seen a microwave before?
No.
Have you ever? You know how when you see a microwave, there are like there's like this like sort of like these holes in the window, right?
Put an object or even an atom in motion, and is that motion what causes the heat?
Yes, you can think about it that way. That is. It turns out that these kinds of radiation don't just heat something; they actually like rip the electron off the proton. Yeah, like for example, infrared. If you're in the sun and you feel like the heat, this is basically how it works. It's slightly more nuanced than that, and we can. I think I'll get into slightly more nuance than that, in the astro lecture or thermal lecture. Okay, yeah.
But the last thing is like, whenever people say that like radio waves cause cancer, cell phones cause cancer, microwaves cause cancer, that's all wrong because those wavelengths cannot rip electrons off atoms. And the way cancer is caused by ionizing radiation is if light hits your DNA, it rips electrons off of your DNA. And that shreds your DNA and causes mutations, which for the biomajors in your audience, like you have your cancer genes and like mutations to those can cause unregulated cell growth. But basically, radio microwaves, radio microwaves and that end of the spectrum cannot ionize atoms, and so they can't cause cancer. All they can do is heat up stuff.
Yeah.
So.
Yeah. That's about it. Any more questions? Yeah.
So like, why is microwaves so special that they use them to heat food instead of like?
That's a good question. It turns out that the frequency that they use in order to heat up microwaves happens to be about the right frequency. So we'll learn about something soon called resonance. But basically, you can think about it as like if you're on a swing, and if you're pushing the swing at like if I just push the swing like randomly, the person on the swing isn't going to actually swing, right? You have to push it at the right like times. And so the same is true of waves. Like if I like push the molecule of H2O at the right frequency, the molecule will end up vibrating.
What does that have to do with that constructive?
It does have to do with that, but it does actually have to do with that. But it turns out the frequency that they the frequency that they use, the wavelength that they use for microwave, happens to oscillate the wave at a frequency that corresponds to the resonant frequency of H2O molecules, and so that's why it heats up H2O well, and that's how microwave works. Yeah, that's a good question.
Yeah, if you have any more questions, you can ask us afterwards.
Yeah, that's technically the end of class. Yeah.
By the way, remember to fill out the attendance.
Oh yeah, I need to fill up.
And also.